All right, so we're closing in on the end of the class, right? We have today, and we have 3 days next week, and a final on the following Monday, and you'll be through statics. Good job. Okay, so we're going to close out some concepts in friction today and Monday, and then we'll work on some review for the last 2 days of class, I think. Okay, so I could really use your input on things that feel rusty for the final that you'd like some review on. If you could email me those topics, I'd really like to cover what you feel like you need help in. Okay. Today we're talking about wedges, which are just a they're a very simple machine that relies heavily on friction. Okay, so we'll start with a wedge that's crammed against or a block that's against a wall. Okay. Oh geez. And we'll drive in this wedge. Okay. So if I push on the wedge with some load, what's going to happen? This one will potentially slide up, right? It might just stay still. In order for this block, let's label them A and B. In order for block B to move up, where does slipping need to occur? Between the two blocks. Okay, there's going to be some slipping there. Where else will there be slipping? The ground, between the ground and A and the wall and B, right? Okay, so typically in wedges, we neglect a couple things. We neglect tipping. We don't worry about a wedge tipping. Okay, they're usually long and skinny. You don't worry about them tipping. You also typically neglect the weight of the wedge. Most of the time, the wedge is much, much lighter than the thing that it's supporting. So if you think, I feel like the place we experience wedges most frequently is a doorstop, right? The weight of the doorstop of the wedge itself has very little to do with whether it's going to keep that door from closing or not, right? Has a lot more to do with the angle and the surface that it's on, right? Doorstops on ice rinks don't work as good as doorstops on gravel, okay? Because of the change in the friction of those surfaces. So if we know that slipping occurs here, what are some of the forces that I need to include in my free body diagram? Normals, okay? So there's probably going to be some normal at A. There's probably going to be some normal AB. And there's probably going to be some normal at B, right? Now, right here, I've just drawn the one normal. Which block is this really acting on? Maybe it'd be better if I separated these to draw my free body diagrams. Here's B. We're saying that there's a normal at B and that there's this normal between A and B, right? But if I drew the free body diagram of the wedge underneath this, right? So these guys are equal and opposite. What about the forces of friction? Which way do we have impending motion here? If I'm planning on shoving this wedge in, how will friction work? It's going to oppose, so I have P over here on this guy. Friction is going to oppose that motion, right? How about here on the top surface? Same thing, right? What about on this surface? Which direction is friction going along the bottom of block B? The other way, right? So this is the same force, FAB, the force of friction AB, but it's going in the opposite direction, right? Because whatever is pushing the wedge or keeping the wedge from going forward, that same force is pushing the block B against the vertical wall. Okay. So what does that tell us about our normal at B? What does it have to counteract? That force of friction, right? Okay. How about as I go in, is block B is going to go up, right? So that means we've really got a force of friction down, right? Because the force of friction is trying to keep B from going up. It's a lot of arrows, right? Let's count up how many unknowns we have. We have P, 1, force of friction at A, 2, normal at A, 3, normal AB, 4, force of friction AB, 5, normal at B, 6, force of friction at B, 7. 7 unknowns. How many equations can we come up with? 6, 4. Oh. I'm the teacher, I tell you. No, that's not how this works. Okay, so I think that we have, let's look at block B first. We have some of the forces in the X equals 0, some of the forces in the Y equals 0, right? We said we weren't worried about tipping, so we really can't sum our moments. So down here we can say some of the forces in the X equals 0, some of the forces in the Y equals 0. We only have 6 equations again. Excuse me, 4 equations. Thank you.
We can still find the force of friction because we have normals. So
Daniel's got something. He says, hey, we could probably find the force of friction because we know normals. Right? So in order for this guy to move, the force of friction, right at the point that it moves, is going to have to be the mu static times the normal. So the force of friction at A is going to be mu static times the normal at A. The force of friction AB is going to be mu static times the normal AB. And the force of friction at B is going to be mu static times the normal at B. And now we have 1, 2, 3, 4, 5, 6, 7 equations. Right? But still no numbers, indeed. Okay? So let's do a problem with some numbers so we can work on our veggies. And I would appreciate it if all of the problems, when you're working on them, you refer to them as veggies. They're veggies. Veggies. I'm saying wedges with a V. Veggies. Just makes it more fun, right? We could do this boringly, or we could make up silly words like veggies. Okay? Yes, about Glakid. I did look it up. It is an antiquated medical term. It's associated with glacial. It is not in common use, but it is indeed a word.
what's it mean?
It means that your facial expressions are somewhat frozen. A Glakid look is you're not communicating anything, you're just like kind of vacant. Okay, so it means your face is an iceberg. Okay? All right, so I kind of freaked out a little bit that I'd been using a word that wasn't a real word. It is a real word. I'm just a few centuries behind the times. Okay? So, next time you go to your doctor, please ask them, Doctor, have you heard the word glaikid? And hopefully they will respond in the affirmative. If not, apparently they're not up on their bloodletting and other 18th century forms of medicine. Yeah. All right, so let's do a problem. I'm going to find you a problem here. Oh, this one looks like a good one. I am sure about this. This looks great.
I like the one above it a lot more.
Okay, so let's go ahead and... Have you guys watched any of my recordings recently on slow speed so that you can have a drunk history version of statics?
Only at 2 times speed, and then I'll do it down to normal speed, and it's pretty much the same.
If you should go the other way, slow it down to half speed and enjoy drunk history statics. Okay? So if the beam AB is loaded as shown, determine the horizontal force P, which must be applied to the wedge in order to remove it from under the beam. The coefficients of static friction at the wedge's top and bottom surfaces are mu CA 0.25 and mu CB 0.35, respectively. If P equals 0, is the wedge self-locking? Ooh, so we didn't really talk about self-locking. What do you think self-locking means? It won't move, right? It doesn't need a force to hold it in. Neglect the weight and size of the wedge and the thickness of the beam. Ooh, that is a good question. What is point C? C is the wedge. Yeah. Yeah, C is definitely the wedge. Okay? So go ahead and put this in your notes, draw your free body diagram, and I'll do the same thing. This kind of gives me an idea of doing a monster problem where you have to like draw the shear and moment diagrams of a beam and figure out the load on the wedge that's holding the beam up, and then maybe some other things. That'd be fun.
I mean, it'd be great for extra credit, but please don't understand.
So what do we need to do first in tackling this problem? Find the load on the top? Seems reasonable. So, yeah. I'm going to unfreeze and go back to my picture here. How many free body diagrams do we need to write? 2. Okay. First free body diagram is going to be the beam. Okay. The beam looks like it'll have dy, dx, it'll have some normal over here. If I'm trying to pull the block out, which way is the force of friction acting on the end of the beam? the same way as it's being pulled. Right?
The force is transferring a little bit.
Excuse me?
It's like the force is transferring a little bit, although it's in different directions, not the same direction.
Yep. Okay. So let's see if I got everything on that free body diagram. I think so. Let's draw another one. Let's draw the free body diagram of the veg. P, force of friction trying to keep it in. Normal at A. Normal at B. Force of friction at B trying to keep it in, right? Doesn't this look fun? Excuse me just a minute. Sorry about that. Little family emergency thing, but it's all right. Yeah, sort of. So we have, I think we have one more unknown in this case, right? 1, 2, 3, 4, 5, 6, 7. Oh no, we have the same number. So where should we start? Let's start with the beam. I think that's a good choice. Okay, so we'll start with the beam. Let's break this into some forces, right? Where would the resultant of the distributed load happen? Or which part, right? So exactly, good question. We'll have one here and one there, right? Magnitude of this guy is the area underneath it, which would be 4. Oh, I didn't include those. Looks like it's 4 meters. Right? So the magnitude of this is going to be 16. What's the magnitude of this guy going to be? Look at you. Thank you. I'm going to need your help. Yeah, really, I'm going to need your help. All of it. What do I do now? Did you say the moment at A? Here or here? At D? Yeah. Okay, so this is a stylistic, right? We could choose how we do it. I would actually choose to sum the moments here because I'd have to use trig in both of these if I did it over here, right? Because each of these would have a component in X and Y. Whereas if I sum my moments right here, I don't have to use trig in my moment equation, right? I'm a highly motivated, lazy person. You got to remember that. If you do it at D, you get brownie points. Only if you get it right. Yeah? Okay. So let's actually start with some of the forces in the X equals 0. So in the X, it looks like I have dx plus what? I said I needed your help. That's the only thing that has a force in the X direction?
Oh, and A.
The normal at A's?
Yeah.
What about the force of friction at A?
Oh, yeah,
That too. Okay, so force of friction at A times cosine of 10 degrees. We were told that this wedge has 10 degrees. Minus NA, sorry, that's NA sine 10 degrees. Equals 0, right? Do I have everything in the X? Yeah? Okay. Sum of the forces in the Y equals 0. Thank you. Cosine, right?
Why is it cosine?
For A, because we're looking for the piece that goes, we're in the Y direction, so we're looking for the vertical piece. And the 10 degrees is now here, right? Trig confuses me too. Absolutely.
I have to think about it.
Okay. 1, 2, 3 unknowns, right? Let's go over to this guy. Sum of the forces, the X has to be equal to 0. P minus the force of friction at B minus the force of friction at A cosine 10. Is that it? Plus the normal at A sine 10, right? So sum of the forces in the Y, I have the normal at B minus the normal at A cosine 10 minus the force of friction at A sine 10 equals 0. So now I have 1, 2, 3, 4, 5, 6, 7 unknowns and 4 equations. These are my friction equations, all right? Problem is, I think I only have 2. Right? I can say that the force of friction at A is going to be 0.25 times the normal at A, and the force of friction at B is going to be 0.35 times the normal at B. Yep. We can come back to this one in some of the moments, right? I certainly can, but that's still, we still have one too many unknowns. So the question was, I could substitute these in. Yes, you can, but still I have 2, 4, 6 equations and 7 unknowns. So the 7th equation I'll come up with is I'll sum the moments, and I'm going to choose again to sum them about A and set them equal to 0. Okay. If I sum them about A, I'll have minus dy times 7. You do the rest and tell me what you get. Now I want you to finish the equation and then tell me. Yes, sorry. Yeah.
Usually so high.
So you add 16.
So I was thinking that I heard languages come out that they have like 4 minutes like mixture. So maybe they have 4 software backing it up.
What'd you get for the equation?
Okay, 16 kilonewtons times 2 meters.
Positive or negative? Positive 16 kilonewton. That'd just be 16 kilonewtons, sorry. Yeah, right here, yeah. 16 kilonewtons times how much?
2 meters.
2 meters. Okay, what else?
6 kilonewtons times 5 meters. Okay, so it would be 2/3 towards something like that.
Yep, it'd be 1/3, 2/3, so we know that it's going to be 2, 1, so it'd be 1 plus 4 is 5. Yep, I agree with that. And that's it, right? Okay. So with these 7 equations, we can solve for the simple veg, right? Not so simple veg. Is the answer yes? No, I think the answer is we need to find out how much load it takes to pull this out, right? So if you solve this, what do you get for P? Oh, this will be fun. Stick it in your calculator, and I expect you all to get the exact same number. Okay? I'm serious. You're going to have to do these. You're going to have to do them on exam, so I want to see that you can do them. Okay, so we do have 7 equations, absolutely. You also, rather than doing that, you could reduce it by 2 to just have 5 equations by making the substitutions wherever there's force of friction at A, just putting in 0.25 in A. Sorry, it's so much thinking.
Yeah, I can do that. 1, 2, 3, 4, 5. Look, a short-term memory. How many variables are there? Just 5. 1, 2. Wait. You can either have 5 variables and 5 equations, or 7 variables and 7 equations. Which one would you like? 5. Yeah. So figure out how you get there. 5 variables. It's always so confusing when you do them. X, Y.
Literally have a full alphabetic expression.
I do. That's why it's hard. There's so many to choose from. Can't do dx. Yeah, you can do dx comma dy. Wait, bro. Yeah, I'm about to say that was so fucking simple.
got answers yet? Yeah, but I don't know if they're right. What'd you get for P, Brendan? P. 5.4. Okay, I'm gonna start putting people's names next to their answers. Up the ante just a little bit.
I got 5.53.
You spelled my name right.
Heck yeah, I spelled your name right.
Thanks a lot. Doesn't always happen.
Bueller. Bueller. Did you get something, Lance? You got a negative answer. No, what's your negative answer? It's getting interesting. Oh, you have to put in, if it's saying P times something else, you have to put in that you specifically want P. So you need to do like curly brackets. I want X, Y, Z, T, and R, whatever you used, and close the curly brackets. Then it should solve for all of them. Really? Hmm. Ah, here it is. It's this A cosine that you have. It's interpreting that as a as something funky. So I think if you put in a multiplication sign, same thing here. Yeah, it really doesn't like letters in front of trig. It's not very bright that way. Is my experience, at least.
I can do it. You don't have to do it.
Oh no, I can push people's buttons with the best of them. I learned it all from Brendan. Let's see what we got. All right, which one's P or P should be P?
Yeah.
5.53 says Lance. Anybody else get 5.53? I know Brandon did. All right, I'm gonna go with 5.53. Isn't that awesome that it turns out that engineering is a democracy, like majority rules? It's not, actually. This is definitely, there's a right and a wrong. Not a difference of opinion, there is a right and a wrong on this problem. Just so you know, Brendan, there's a right and a wrong, and you are wrong. Okay? It's up for debate. No, it is not up for debate.
There's 3 people who got answers. Maybe those don't start to say
The standards organization just need to take a vote on this stuff.
Yeah. All right.
You see the new Cybertruck?
I did see the new Cybertruck. You want me to draw a picture of it? Because I can. This is what the new Cybertruck looks like.
Oh, dude, I saw the commercial for that.
Look at that.
Yeah, it looks
No,
I should be a designer for Tesla. I could make a lot of money. I bet.
the guy that was interviewing him or like presenting it, he's like, Elon Musk is known for not meeting deadlines or not giving people what they want, but he's getting through on this one.
Yeah.
You also see how they're talking about how the glass is indestructible.
Yes.
And then he just
That was awesome.
And then, so they're like, let's test the other one, did this exact same thing.
And they're just like,
Bummer, dude.
It's just like, there's always room for improvement.
Isn't that interesting, though? So I guarantee you what happened is they had engineers test it before they did that on stage. But the engineers are like reluctant to break it, so they're kind of being gentle. Whereas that guy's like, you told me to throw a ball at it, okay, whack, right? So it shows you should not always test your own stuff. Have somebody else do it. It's the most aggravating thing in the world, at least for me, when I have a product that I've developed and I then give it to somebody else to test and it doesn't work right. I'm like, it's because you're using it wrong.
It's your bias, like.
Well, and it's interesting. I make it their fault rather than, okay, I designed it so that it works for me, but it doesn't work for them. So I have to go back and be like, all right, if it doesn't work for them, they're the customer, not me. So I have to make it so that even an idiot can use it.
Yeah, but the ball they dropped from high, it didn't break the glass. Did you see that?
I didn't.
Oh, they tested like not on the truck, but like another piece of glass.
Oh, yeah.
The same glass.
Yeah.
And they like dropped the same ball like from really high up. And
You have like you threw the ball at like a higher velocity because there's rock.
That's weird. That would be super embarrassing, though, if someone didn't tell them, yeah, we're putting in the cheap glass and the... Whoops. Oh, yeah, so we didn't answer the question, did we? Right? So the question was, is this a locking wedge or not? How do you know that it's a locking wedge?
because we know from the problem that P is 0, and also by solving it that P has to be greater than 0 to move it.
Yeah, so we know because P, in order to move the wedge and pull it out, we have to apply a force of 5.4 kilonewtons. So we know that if we don't apply that, that would mean it's staying still, so it's self-locking, right? So that's why I was interested, Lance, when you got a negative answer. Because if there was a negative answer, then that would tell us it doesn't take anything to pull the wedge out, it's being shot out, right? Okay, so good question.
That'd be pretty fast.
Well, interesting, Brendan. So Brendan and Brandon shouldn't sit next to each other. Brendan is saying that a wedge being shot out at 5.4 kilonewtons would be pretty fast. Depends on how much mass it has. Could be really slow, right?
But we're also assuming it's a wedge, it's probably really light.
You know what assuming does.
It's just a doorway.
Okay. All right, so we're pretty much out of time. I'm pretty discombobulated today, so I'm going to go ahead and tell you what I'd like you to do over the weekend is this problem right here. Okay?
We have a great problem.
You will not have a graded problem this week.
We won't have a quiz.
We won't have a quiz. We just haven't covered enough material really to merit a quiz. So actually I'll make it class's choice, but it's not person's choice. This will become a democracy momentarily. Would you like to have a graded problem due on Monday? Raise your hands if you would not like to have a graded problem. Would prefer not to, if you would prefer not to have another graded problem, raise your hand. Okay, the majority would prefer not to have another graded problem. If you would prefer not to have another quiz on a week from today, raise your hand.
But will it be really easy?
No. Okay, so we will not have a quiz, we'll not have a graded problem, student's choice. What we're going to do then on Monday is go over screws. So we have wedges and screws, because the screws are just an application of wedges that are wrapped around a cylinder. It is 865. 865, 866. Okay? So that's what we'll go ahead and get ready for Monday. Okay? And then we'll look at the screws, and that will kind of wrap up the content. I really do mean it. I want you to tell me what you want reviewed on Wednesday and Friday.
On Monday, tell you.
Yeah, Monday's fine. You can tell me on Monday. Okay? Have a wonderful Thanksgiving.